Hello everybody. This is the third part of the lecture on acid-base disorders. All of you have by now know what is metabolic acidosis. Metabolic acidosis is when acid accumulates in the body and the bicarbonate is used up. There is a bicarbonate deficit and this results in what is known as metabolic acidosis. The pH decreases below 7.35. Now I'm going to talk to you about the anion gap, which I had already mentioned to you in my earlier video. The anion gap is calculated by subtracting the major plasma anions, that is the chloride and bicarbonate, from the major plasma cations, that is sodium and potassium. The normal range varies from 8 to 16 milliequivalents per liter. This value represents the amount of unmeasured anions like ketones or lactate which may be present in the plasma. So, how is the plasma anion gap calculated? This is by adding the concentration of sodium and potassium, and we add the concentration of chloride and bicarbonate. The difference between these two will give us the anion gap. Now, based on the anion gap, metabolic can be divided into two main groups. One is the high anion gap, which is known as the HAGMA, and the normal anion gap, which is known as NAGMA. Now, to represent the three types of anion gap, you have the situation A, where the anion gap is normal. That is, we have a normal sodium level 138 milliequivalents per liter, and the potassium level would also be normal, maybe around 4 or 4.5 milliequivalents per liter. The level of chloride is 105, the level of bicarbonate is 25 milliequivalents per liter. So the anion gap works out to be around 12 milliequivalents per liter. So this is a normal ion distribution. In the second case, that is case B, we find that the bicarbonate levels have decreased. Okay, so as you can see in the figure here, we find that the bicarbonate level has decreased. There is a decrease in the bicarbonate level and there is an increase in the anion gap. So this is known as the high anion gap metabolic acidosis due to acid accumulation, decreased bicarbonate and increased anion gap. In the third situation, we find that the anion gap is normal, but the bicarbonate has decreased and there is an increase in the level of chloride. So this is known as NAGMA, or normal anion gap metabolic acidosis. This metabolic acidosis is due to a loss of bicarbonate ions. So there is a decrease in the bicarbonate due to bicarbonate loss, and there is a normal anion gap, but to make up there is an increase in the level of chloride ions. So all of you are now familiar with the calculation for anion gap. Example 1 is a normal situation where we have normal levels of sodium 140, potassium 4, chloride 114 and bicarbonate 18. So when you look at the difference between the two, you find that the anion gap is normal, that is 12. In the second case, we find that the total of sodium and potassium is 144, whereas the total of chloride and bicarbonate is 114. That gives a difference of 30, which is a very high anion gap. Now, what are the clinical conditions where we see a high anion gap? So one of the clinical conditions where we see a high anion gap is diabetic ketoacidosis. This is one of the most common conditions where we see a high anion gap metabolic acidosis. Similarly, we can see it in the case of starvation ketosis, lactic acidosis and renal failure. A normal anion gap metabolic acidosis is when there is a loss of bicarbonate, as we can see in the case of severe diarrhea and renal tubular acidosis. Another terminology which we need to know is that of the osmolar gap. What is the osmolar gap? It is the difference between the measured plasma osmolarity and the calculated osmolality. The normal is less than 10 milliosmolars, and a raised anion gap, metabolic acidosis, and an increased osmolar gap is suggestive of acute poisoning with either methanol or ethylene glycol, etc. What are the clinical manifestations of metabolic acidosis? When you look at the respiratory system, you have an increased alveolar ventilation, that is, increased carbon dioxide excretion. If you look at the cardiovascular system, we find that there is decreased myocardial contractibility, okay, and ventricular arrhythmias, particularly when the pH goes well below 7.2. There is also decreased vascular resistance and impaired response to catecholamines. If you look at the gastrointestinal system, typically we see nausea, vomiting, abdominal pain, and in diabetic ketoacidosis, we can see diarrhea and uremic acidosis. What is the treatment? Ketoacidosis means we have to give IV fluids, and if it is diabetic ketoacidosis, we have to give insulin, and we should make sure that there is potassium replacement. Lactic acidosis, oxygen may be given. Now, since there is loss of bicarbonate or a deficit of bicarbonate, the amount of bicarbonate to be given should be very carefully calculated. The potassium status has to be monitored very closely and promptly and corrected. Now, what is the relationship between potassium and diabetic ketoacidosis? The hormone insulin increases the potassium uptake by cells. So, patients with severe uncontrolled diabetes, that is, with metabolic acidosis, is usually hyperkalemic. When such a patient is given insulin, it stimulates potassium entry into the cells. So, when it moves into the cells, what happens? The plasma potassium level is depleted, resulting in hypokalemia. So, if this is untreated, it can affect heart functioning and is life-threatening. So, in the treatment of diabetic ketoacidosis, if potassium has to be given, it should be very closely monitored. Now, there is a relationship between potassium and alkalosis. Hypokalemia leads to an increased excretion of hydrogen ions. Okay, so when there is potassium level goes down, to maintain the acid-base balance, there will be removal of hydrogen ions or increased excretion of hydrogen ions, and this can ultimately result in metabolic alkalosis. Conversely, in metabolic acidosis, what happens? This is associated with increased renal excretion of potassium ions in an attempt to conserve hydrogen ions, and this can lead to hypokalemia. So, as you can see, plasma potassium concentration is therefore very significant in acid-base disorders, and potassium supplementation, if given, should always be carefully monitored. Now, another way of classifying metabolic alkalosis is to look at the urinary chloride. Why is this useful? If the urinary chloride is low, that is less than 10 millimoles per liter, it indicates that this alkalosis may be due to volume depletion. So, this could be due to prolonged vomiting, it could be due to nasogastric suction, it could be due to upper GI obstruction. And such cases will respond to saline infusion. If, on the other hand, the urinary chloride is high, greater than 20 millimoles per liter, the alkalosis is likely to be due to hypokalemia or an excess of aldosterone, and this will not respond to saline infusion. Lastly, there could be a mixed type of acid-base disorder. The patient may have 2 or more acid-base disorders occurring simultaneously. That is, for example, a patient may be present with chronic renal failure. So that patient would definitely have primary metabolic acidosis. This patient may also have chronic obstructive airway disease, and so the patient may have respiratory acidosis. So pH will be decreased, but bicarbonate and carbonic acid levels may be altered. Certain compensatory mechanisms can also sometimes lead to mixed type of disorders. So this is a good mnemonic to remember what happens in acid-base disorders. ROME, R for respiratory, and in respiratory conditions you find that it is opposite. That is, in case of alkalosis, pH is increased, but PCO2 is the opposite, it gets decreased. In respiratory acidosis, pH is decreased, but the opposite occurs to PCO2, it is increased. In case of metabolic, we find that it is equal, that is, both go up or down in the same direction. That is, in metabolic alkalosis, both pH and bicarbonate goes up, and in metabolic alkalosis, both pH and bicarbonate goes up, whereas in metabolic acidosis, both pH and bicarbonate will go down. ROME, a mnemonic to remember the acid-base disorders. Now, blood gas measurements can be measured by means of a blood gas analyzer. It is of great value in assessing blood gas status. The arterial blood is used to measure acid-base parameters. The blood has to be transported very quickly to the lab to be analyzed and interpreted. Now the normal values I've given: bicarbonate 22 to 28 milliequivalents per liter, PCO2 between 35 to 45 millimeters of mercury, and partial pressure of oxygen 90 to 130 millimeters of mercury. Thank you.